Hi there, virtual VMSG. Today I'd like to tell you about the results of a new study that we've just had published in GCA that's looking at boron isotopes in melt inclusions from Iceland. We know that volatile and trace element heterogeneity in the Earth's mantle is influenced by the subduction cycle, and the basalts erupted at ocean islands like Iceland can sample that recycled subducted material. The aim of this study is to see if we can use boron isotopes to identify the signatures of recycled material in the Icelandic mantle. And to do this, we measured boron concentrations and boron isotopes in two sample suites, one from the Reykjanes Ridge and one from North Iceland. This diagram shows the boron contents and boron isotopic compositions of key geological materials in a subduction zone. Depleted mantle has a low boron concentration and a boron isotopic composition of about -7 per mil. When we melt this to produce morb, boron behaves as an incompatible trace element, but isotopic signature is not fractionated. The oceanic crust then interacts with seawater, which has a very heavy boron isotopic signature, and this means that materials entering the trench have a very high boron concentration and a very heavy boron isotopic ratio compared to depleted mantle. This means that recycled subducted material has the potential to exert strong influence over the mantle's boron concentration and isotopic composition. We'll start by looking at samples from the Reykjanes Ridge. These sample mantle heterogeneity approaching the Iceland plume. This graph shows that the strontium isotopic signature of the Reykjanes Ridge glasses remains relatively constant until 61 degrees north, at which point there's a strong kick upwards in the strontium isotopic ratio that signifies an increasing contribution of enriched mantle material associated with the Iceland plume. The contribution of the enriched mantle component is also recorded in the concentrations of incompatible trace elements such as praseodymium. Everything in this grey shaded bar records the influence of the enriched mantle component approaching Iceland. Interestingly, we don't seem to see any influence of the enriched component on boron concentration nor on the boron isotopic ratio of the Reykjanes Ridge basalts. This suggests that whatever the enriched component is, it's not contributing very strongly to the boron budget of the Reykjanes Ridge basalts. We applied some fairly stringent filtering criteria to our Reykjanes Ridge data to make sure that we weren't considering any samples that could have gained boron by interacting with seawater. The resulting dataset is the black points in the diagrams. These yield a new estimate for the boron isotopic composition of Reykjanes Ridge mantle, -6.1 per mil. This is different from global morb, which has been estimated at -7.1 per mil, although the two ranges do overlap within uncertainty. We'll now turn to olivine and plagioclase host melt inclusions from North Iceland, which sample mantle heterogeneity close to the plume centre and on the length scale of individual eruptions. The map on the left shows the locations of the samples, and the colour scheme is the one that I'll use throughout the rest of the talk. The samples come from the Askja and Barðabunga volcanic systems. The two samples to keep your eye on are the yellow circles, which are a basaltic tuff sequence from Askja central volcano, and the blue diamonds, which come from the older Holothrain eruptions. This plot shows boron concentrations in our North Iceland melt inclusions and matrix glasses plotted against magnesium oxide, which is an index of fractional crystallization. The most primitive melt inclusions contain the lowest boron concentrations, and boron generally behaves as an incompatible trace element during fractional crystallization. You can see that there's some variation in boron concentration at constant magnesium, which can't be explained by a simple fractional crystallization relationship. Here I've plotted boron against a similarly incompatible trace element, praseodymium. The boron-praseodymium ratio of normal morb is shown in the grey shaded area. Our North Iceland samples have a much lower boron-praseodymium ratio than typical morb, which tells us something about the composition of the mantle source. Interestingly, our Reykjanes Ridge basalts have higher boron-praseodymium than normal morb. The North Iceland melt inclusions show big variations in their boron isotopic ratios. Some of the melt inclusions have delta 11b that's similar to morb, but more frequently they're isotopically heavy or isotopically light. The wide spread of boron isotopic ratios within a single eruption is also a little bit alarming. It suggests that some of these melt inclusions are not in fact recording a primary mantle-like boron isotopic signature. Fortunately, we can check this. On the left, I've plotted boron isotope ratios versus magnesium oxide for olivine-hosted melt inclusions, and in black, I've added some data from the western volcanic zone from a previous study. Fractional crystallization at high temperatures should not fractionate boron isotopes. The fact that our boron isotopic ratio seems to be increasing as fractionation proceeds tells us that there's another process going on. This is also recorded in the oxygen isotope ratios of our North Iceland melt inclusions, which are not consistent with a simple fractional crystallization story. We can therefore screen the melt inclusions to include only the primitive melt inclusions with more than 8% MgO. Only these melt inclusions are likely to record a mantle-like delta 11b. We can now use these high magnesium melt inclusions to say something about the Icelandic mantle. Here I've plotted delta 11b against the lanthanum ytterbium ratio, which I'm using as a passive tracer for the composition of the mantle source, since lanthanum ytterbium is not expected to be fractionated during partial melting. You can see that for the Icelandic melt inclusions, there's a broad, although relatively poorly defined, positive correlation between lanthanum ytterbium and delta 11b. The kernel density estimates show the probability distribution for boron isotopic compositions of particular eruptions. Let's start by looking at Holuhraun. These melt inclusions are relatively depleted, and they have a peak in the probability distribution at minus 10.6 per mil. This points to an isotopically light mantle source. Isotopically light boron is consistent with the presence of a dehydrated subducted component in the Icelandic mantle. The plot on the left shows a numerical model that describes how slab dehydration and dewatering fractionates boron isotopes and drives the residue in the subducted slab to isotopically light values. Importantly, because the boron is being partitioned into the fluid, actually the slab itself has quite a low boron concentration. But because its isotopic contrast with depleted mantle is so big, it doesn't take a lot of this subducted material to significantly modify the boron isotopic composition of the bulk mantle. Other studies of melt inclusions from ocean islands have also concluded that light boron isotopic signatures are consistent with melting of a dehydrated slab component. The green points in this plot on the right show melt inclusion averages for eruptions from La Palma in the Canary Islands, which are best explained by mixing of melts from a dehydrated slab component and melts from an ambient morb component. The more enriched population of our North Iceland melt inclusions has a boron isotopic signature of minus 5.7 per mil. That's indistinguishable from our new estimate of the boron isotopic composition of Reykjanes Ridge mantle. We think that the enriched component sampled by these enriched melt inclusions is likely to contain dehydrated lithosphere, but we think that recycled component is likely to contain almost no boron, so that the melt's boron content is diluted by the recycled component rather than enriched. We've already seen that the North Iceland melt inclusions must have been modified by crustal assimilation. This is the only way to explain the variation in boron concentration at constant MgO and the trend that we observe between MgO and delta 11b. To produce these trends, the contaminant should have a high boron concentration and heavy delta 11b. However, analyses from drill cores show that the Icelandic upper crust has extremely heterogeneous delta 11b, which means that the crustal end member composition is largely unconstrained. With this caveat in mind, we've calculated parabolic mixing curves between our Iceland mantle end members and potential contaminants that could exist in the Icelandic upper crust. The boron isotopic compositions of our more evolved melt inclusions can be modelled by less than 5% up to 20% of crustal assimilation, and even a small amount of assimilation can significantly modify the boron isotopic ratio. This means that if you want to measure the boron isotopic composition of a mantle end member, you must carefully screen your melt inclusion population for any evidence of crustal assimilation. I'll leave you with the main conclusions of our paper. Please check it out if you'd like some more information. Thanks very much for your attention, and I look forward to your questions.